Hi, this is Tzvi Rosen. Today we're going to be talking about two theorems about ideals and commutative rings that show up in Chapter 1 of Atiya MacDonald. And they don't get too much fanfare, but they're actually very well-known theorems with names and Wikipedia pages, and they are the Chinese Remainder Theorem and the Prime Avoidance Lemma. Let's start with the Chinese Remainder Theorem, and we just need a few prerequisites. So we're going to define the direct product of rings as follows. If we let A1 through AN be rings, then we define the direct product of rings to be the set of sequences x1 up to xn, where xi is in AI, and we're going to give this set operations of component-wise multiplication and addition. And we're going to call this ring the direct product. Okay. So that's the direct product of rings, and the other definition we need is coprime ideals. So if we have two ideals in a ring, so let A and B be ideals in a ring A, we say that A and B are coprime if A plus B, the sum of ideals discussed in the last lecture, is equal to the whole ring, or the ideal generated by the unit element. Okay, so that's how we define coprime ideals. Okay, now with the definition of the direct product and coprime ideals, we can state the Chinese Remainder Theorem as it shows up in Atiya MacDonald. And it's in proposition 110. Let A be a ring with A1 through AN in A ideals, and define a homomorphism phi from A to the direct product of the quotient rings A mod AI, where I goes from 1 to n, by the rule that phi of x maps to x plus A1 up to x plus AN. So you can view this as just elements of the quotient ring in the standard way. Then we have the following results. If AI and AJ are coprime, whenever I is not equal to j, then the product of the ideals is equal to the intersection of the ideals. That's first. Second, if we have that phi is surjective if and only if AI and AJ are coprime, whenever I is not equal to j. And finally, phi is injective if and only if the intersection of the ideals AI is equal to the zero ideal. Okay, and we'll see the power that this theorem has after proving it. But let's start with the proof of part 1. Okay, so first we want to show that if the AI are coprime, then we have that the product of the AI is equal to the intersection of the AI. So for this, we have to take it in two phases. First, consider the case n equals 2. So here we just have two ideals, A1 and A2. Coprime, and we want to show that A1, A2 is equal to A1 intersect A2. Okay, so to start this off, we observe that one of these directions is very straightforward. So this, because A1 and A2 are closed under multiplication by elements of the ring, A1, A2 is certainly contained in both A1 and A2. So A1, A2 is in A1 by closure under A multiplication. Okay. Similarly, A1, A2 is contained in A2, but that gives us that it's contained in the intersection. Okay, as for the reverse inclusion, here we have to be a little craftier. And we note that because A1 and A2 are coprime, we have A1 plus A2 will be equal to 1. Okay, and now we can consider what happens when we multiply. So we're trying to show that the intersection is contained in the product. So let's consider what happens when we take A1 intersect A2 and we multiply it by A1 plus A2. Okay. So you can check that this product distributes. And so we're looking at A1 intersect A2 times A1 plus, let's give ourselves a bit more room here, plus A1 intersect A2 times A2. Okay, so now we have this sum of ideals, and we can observe that we'll notice in the first summand, A1 intersect A2 is contained in A2, so the product is contained in A1, A2. Similarly, in the second term, A1 intersect A2 is contained in A1, so that product is contained in A1, A2. So let's grab that. So this is contained in A1, A2. But what we started with is A1 plus A2 is equal to 1. So this implies that A1 intersect A2 itself is contained in A1, A2. Okay, and that shows equality. So we have the base case of n equals 2, and now we want to prove it's true for larger values of n. Okay, so let n be greater than 2. We can take the product up to n of the ai and observe that this is equal to the product up to n minus 1 of the ai, and then multiplied by an. And similarly, the intersection up to n of the ai is equal to the intersection up to n minus 1 of the ai intersected with an. But applying the induction hypothesis, so if we apply the induction hypothesis, we have that these two things are equal. So we can call it B, so B is equal to the product of the AI up to n minus 1, and it's equal to the intersection up to n minus 1 of the AI. Okay? And now, all that's really left to do is to show that if we take B and AN as a pair of ideals, if they satisfy the hypotheses of the theorem, specifically that AN and B are coprime, then that will prove that the intersection is equal to the product. So we just want to show that AN B is equal to AN intersect B, and so it's sufficient to show that they're coprime. AN and B are coprime. Okay. Okay, so suppose that we have AN, so B is equal to the product of all of these ideals up to n minus 1. So we know that each of these, with respect to AN, is coprime with AN, each of those AI. So what does that mean? That means for each I, there exists xi in AI and yi in AN such that xi plus yi is equal to 1, okay, by virtue of their coprimeness. But that means that yi is congruent to one minus xi mod AI. And that means that, in particular, that the product of the yi, which is obviously in AN, is going to be congruent to 1 mod B, right? Because that's the product of the AIs. And that means that you can find something in B to add to the product of the yi's to get 1. And that means that AN plus B is equal to the 1 ideal, which tells me they're coprime, which is all we needed. Okay. Next, we proved that phi is surjective if and only if AI and AJ are coprime for all I and j, and I not equal to j. So let's start in this direction. So assume that phi is surjective. We can show that each pair of ideals is coprime. So we know that if phi is surjective, 1 zeros must be in the ideal, must be in the image of phi. But that means that there's an x such that x is congruent to 1 mod A1, and x is congruent to 0 mod A2. Okay. Okay, so if we take 1 minus x, that's going to be in A1, and x is obviously in A2. And if you add them together, 1 minus x plus x equals 1 must be in a1 plus a2, which proves coprime. Okay, and by symmetry, this argument works symmetrically for all other pairs. So ai, aj, coprime for I not equal to j. Okay, how about in the other direction? So here we're going to suppose that all of the pairs of ideals are coprime, and we want to show that every point is in the image, every element is in the image of the map phi. So it'll be enough to show, enough to find some x such that phi of x is equal to the 1, 0, 0 point that we had before. Okay, because by symmetry, if you have one of these for each coordinate, you'll be able to generate any point just by scaling. Okay, so how do we find this x? Well, we know by coprimeness that there exists ui in ai. Actually, let's make that ui in a1 and vi in ai for I between 2 and n, such that ui plus vi is equal to 1. Okay. So now let's use these ui's and vi's to, and that's by virtue of coprimeness, of course. So let's use these ui's and vi's to generate some x, which will give us our point under this mapping. Okay, so we want something which is equivalent, which is congruent to 1 mod a1, and which is in all of the other ideals. So because vi is equal to 1 minus ui, so this is congruent to 1 mod a1. So that means that the product from I equals 2 to n of vi is going to be congruent to 1 mod a1, but by properties of ideals, it's also going to be congruent to 0 modulo all of the other ideals. Modulo ai for I greater than or equal to 2. And this tells us that phi of this product, vi, is going to be equal to our desired point. Okay, and as we said, that's enough to generate all other points. Okay, so that proves the second part of the Chinese remainder theorem. And the final part is much simpler. If phi is injective, we want to show phi is injective if and only if the intersection of the ideals is 0. We'll consider what it means for phi to be injective. That means, so phi injective is true if and only if the kernel is 0. But what is the kernel of phi? It's something that maps to 0 in all of these quotient maps. But the kernel, so the kernel of phi is something which is the set of x such that x is in ai for all I, for I between 1 and n. But this is plainly just the intersection of the ideals. Okay, so we have proven the Chinese remainder theorem. So how do we apply this? let's say we want to count some set which is very large. Let's say on the order of 20,000. You don't know exactly how much it is, but let's say you know it's less than 25,000. So you could use the following fact. So the integer 27,720 is equal to 5 times 7 times 8 times 9 times 11. Okay. And taking prime factorization of all of these, so 8 is 2 cubed and 9 is 3 squared, and we have 5, 7, and 11 are prime. And what we can do with this is we can apply the Chinese Remainder Theorem to say that the quotient ring Z mod 27,720Z is isomorphic to Z mod 8 cross Z mod 9 cross Z mod 5 cross Z mod 7 cross Z mod 11. And what does this do for us? This means we could have the elements of the group grouped together in clusters of 8 and then count how many are left over. Then have them grouped together in clusters of 9, count how many are left over, etc. for the other primes. And you'll notice, of course, all of these are co-prime to each other because we group them by powers of primes, obviously. So you would find some n1, n2, n3, n4, and 5. Okay, and this is aided by having the individuals grouped together, so you don't have to actually count all of them. You're just counting the remainder. And this will point to a unique element here. Okay, and so having computed just these remainders, which are all small numbers less than 11, we now know the precise number, anywhere up to 27,719, which is generating those remainders. Okay, and this was the folklore I heard is that this was used to count armies, that you have the soldiers grouped together and then you could count the remaining soldiers to get the tally for the total group of soldiers. But this is also used in computer science applications as a way of cutting down computations. Okay, so that's the integers. That's one ring where Chinese Remainder Theorem is very useful. Another ring is in polynomial ring, where you have just any field k as your ring of coefficients. So then what are we talking about when we apply the Chinese Remainder Theorem? Well, we can say, let's consider our polynomial ring modulo some product of linear polynomials. So x minus ai, where I goes from 1 to n. Okay. Then because any pair of distinct ideals generated by linear form are coprime, the Chinese Remainder Theorem tells us that this is isomorphic to the product k adjoin x minus modulo x minus a1 cross up to k adjoin x modulo x minus an. And so what you might do, if you want to figure out some polynomial that you know has degree less than n, you can just evaluate it, which is essentially what you're doing when you compute these quotients. Evaluate your polynomial at a1 through an, and that's going to specify a polynomial in k adjoin x mod this degree n polynomial. So something like, so b1 up to bn, and this will be an element of kn, this points to a unique polynomial p of x in the quotient ring on the left. And this, I think, is called Lagrange interpolation. The next theorem we'll be working with is the Prime Avoidance Lemma. And this shows up as proposition 1.11, part I, Inertia McDonald. Let P1 through Pn be prime ideals, and let A be an ideal contained in their union. Then A must be in one of the PIs. Okay, so you can't just have it as a union of different prime ideals. It's got to be contained in one of them. Okay, and there's actually a sharper version of this. You don't need all of those prime ideals to be prime. And this shows up in lemma as lemma 3.3 in the textbook by Eisenbud. If you let P1 through Pn be ideals of A, not necessarily prime, and let A be an ideal contained in their union. Suppose either that the ring A contains an infinite field, or all but two of the PI are prime. Then A will be contained in PI for some I. So here we gain, in the case that A contains an infinite field, we gain the generality of none of the ideals needing to be prime. But even if we don't have that, we can still pick up two ideals that don't need to be prime, while the rest of the ideals must be prime. So this is a more general version of the prime avoidance lemma from Eisenbud. Let's prove the statement for an infinite field. And here we'll use a lemma, a vector space over an infinite field cannot be a finite union of subspaces, of proper subspaces. Okay, and how does that affect our case? Well, if you have an infinite field K inside of your ring A, so given K inside of A, every ideal is a K vector space because it's closed under addition and it's closed under multiplication by K. So A must be inside one of them, inside one of the PI. Okay, and we can even prove this lemma. So we'll prove the lemma. Okay, suppose we have V equals the union of Wi, okay, where these are proper subspaces, such that no Wi can be omitted. Okay, and if any Wi can be omitted, then just omit it, and unless you end up whittling it down to a single subspace, you've reduced to a case we can deal with. Okay, no Wi can be omitted. So this means that there must exist an x in W1 such that x is not in any Wi for I not equal to 1. Because if everything in W1 was included in some other subspace, you could omit W1. Okay, so we have x in W1 with this property. And similarly, we have y in the complement of W1, because otherwise W1 would not be a proper subspace. Okay, now we're going to consider the set of x plus alpha y, where alpha is in the field. Okay, so plainly, this has to be contained in V. So this is a subspace of V, or this is contained in V, which means it must be contained in some Wi. Each is in some Wi. But you have an infinite number of elements corresponding to each element of the field, so you're going to have two of these that end up in the same subspace. So we'll have x plus alpha 1y and x plus alpha 2y in wk, or let's use a different letter, wj, with alpha 1 not equal to alpha 2. But then we can cancel the y's. So we can take alpha 2 times x plus alpha 1y. Oh, and I should also note that j is not equal to 1 here, because since y is not in W1, x plus something times y can't be in W1. Okay, so if you have alpha 2 times x plus alpha 1y minus alpha 1 times x plus alpha 2y, you get alpha 2 minus alpha 1 times x in wj, but we know x is not supposed to be in any of the other subspaces except for W1, so that tells us we have a contradiction. Okay, so it must be that you can't have this being a union of proper subspaces. Okay, maybe a little belabored, but hopefully you got the idea. Okay, so now let's consider what if all but two of the PIs are prime. Okay, so plainly if there's only one ideal, so if you have n equals 1, so that's telling us that A is contained in the union of P1, or Pi, where I is just equal to 1. And this is trivially would imply that A is contained in P1. Okay, so ignore the n equals 1 case. Okay, so now taking the induction further, we can always assume that all of the PIs are necessary. Assume all PIs are necessary, meaning, in other words, no proper subunion contains A. Okay, so for n equals 2, if A is contained in P1 union P2, well, these are any ideals, if you have x1 in P1 and x2 in P2, then this means that x1 plus x2, or rather, let's put it this way. If x1 is in P1 not in P2, right, because we can assume that there's something that's in one that's not in the other, otherwise it would be just contained in one of them, and x2 is in P2 minus P1, then that tells us that x1 plus x2 is in neither P1 and P2, implying that it can't be in A, but that means that A wouldn't be closed under addition, so that would be a contradiction. Okay, and now we can consider the case of n greater than 2. Okay, so since we have more than two ideals, we can assume one of them is prime. And let's assume it's the first one. as before, there is xi in pi such that xi is not in pj for any j not equal to I. Okay, this is by virtue of not being contained in any proper subunion, so you must have something special from each of those pi's. Okay, well now if I take x1 plus x2 times x3 dot 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 up to xn, well I know this guy is in p1, and I know that this guy is not in p1 because p1 is prime. So a product of elements not in a prime ideal is also not in the prime ideal. So this element is not in the union. Let's call this y. Y is not in the union of the pi's because it can't be in p1 or in any of the other ones. But that means that a is not closed under addition. And that gives us our contradiction. So we have that a must be contained in one of the pi's. Okay, and you might say, well, looking at this argument, we really only use that p1 is prime. So why is it important that all but 2 are prime? And the reason is that we have this induction hypothesis. So we need to be able to peel away ideals in such a way that the argument will always be true. So unless all but 2 of the ideals are prime, I might get to a situation where I have, by peeling away, so let's say I have 3 non-prime ideals and 1 prime ideal. When I do induction to the n equals 3 case, I might be left with 3 non-prime ideals, and then the argument doesn't work anymore. Okay, and in terms of applications of the prime avoidance lemma, it's hard to find any that are not a little bit more commutative algebraic and theoretical. So I include one here, which in only a few lectures this will make sense to us. If we let R be a Noetherian ring, and M is a finitely generated non-zero R module, every ideal consisting entirely of zero divisors on a module M annihilates some element of M. Okay? So you might think zero divisors, maybe this zero divisor kills something and this zero divisor kills another thing, but not, you won't have the entire ideal killing something. But this theorem tells us that yes, the entire ideal will kill some element of this module. And the idea of the proof is that the zero divisors are contained in the union of associated primes of a module. So the ideal must be contained in one such associated prime by virtue of the prime avoidance lemma. And hopefully that exercise in ideals in commutative rings was fun for you. And we'll see further applications of both of these as we continue in the course. Thanks.